Yeah,
Okay, so it is being done in Allen right now, complex numbers.
yeah, it's being done.
Okay, so tell me, you can till what point has been covered in class?
Uh, I think,
What is the last thing
okay,
they taught?
okay, one sec. I'm not entirely sure. I'm just checking.
Yeah.
Okay, rotation theorem, and I don't know how to pronounce it. Demoibre. That
De Moivre's.
theorem. Yeah, so that is the last thing that's been done.
So this is how many beginners boxes?
This is like just before the fourth beginner box. Like after
Okay.
this fourth beginner box.
Okay. So tell me the doubts. We'll discuss questions and then through that we'll do the theory.
I
So
actually didn't really understand the concepts either. Like the rotation theorem and this one, I didn't really understand.
before that in beginners box 1, 2, 3.
Yeah, I do have a few doubts. Should I send them like the
Yeah, yeah.
pictures? Okay.
Send me on WhatsApp or something.
Yeah.
Okay. Okay. Sketch the locus of a complex number. Sketch the locus of a complex number satisfying log cos 1 mod z is greater than equal to log cos 1 mod z minus 1. Okay, fine. So, uh, send everything, whatever you have. After that, we'll start discussing. That's it. This whole
Uh,
question.
no, I have two more.
Yeah.
Yes. Yeah, these two.
Okay. Okay, fine. So let's look at this one first. Here, sketch the locus of this complex number. So first of all, you have to realize this is a logarithmic inequality. So in logarithmic inequality, it matters whether the base is greater than 1 or lesser than 1. Okay.
Yeah.
So if the base is, if A is greater than 1, then this inequality means that B is greater than C,
Yeah.
right? However, if A is less than 1, then this inequality means that B is less than C, right?
Yeah.
Here the base is less than 1, right?
Yeah. That's the one.
So basically this inequality means mod Z is less than equal to mod Z minus 1,
Yeah.
correct? So now let's think about it in terms of the Argand plane. Like here, mod Z means what? Distance of Z from 0, right?
Yeah.
This means basically this, right?
Yeah.
So distance 0 is here. So distance of Z from 0 is less than equal to the distance of Z from 1, right? So
Okay.
let's mark 1 here, 1 comma 0, and this is 0 comma 0, right?
Yeah.
So if suppose you had this inequality, this equality, right? That would mean it is equidistant from 0 and from 1, right?
Okay. Yeah.
There would be a point in the middle that is going to be equidistant. Also, there are going to be points on this perpendicular line, right? Everything on the perpendicular bisector is going to be equal distance from 0 and from 1, right?
Yeah.
You understand that, no?
Yeah.
If there's a point here, this is same distance as this because this is perpendicular bisector. So
Yeah.
if Z is less than equal to this, that means the distance here is lesser, right? So it is
Okay.
this
Yeah.
side, right? Everything to this side of the line, right,
Yeah.
will have lesser distance from 1, right?
Okay. Yeah.
Basically, the graph will be like this is 0, this is 1, and the midpoint there is a perpendicular bisector at half, right? Everything to the right, to the left of this graph is going to have lesser distance here than here, right?
Yeah.
This is 1 comma 0, correct? So
Hmm.
this graph basically is the half plane to the left of Z is equal to half, right?
Okay. Yeah.
X is equal to half line left of that, correct?
Yeah.
So you have to understand this on the basis of the meaning of mod Z and mod Z minus 1. So
Yeah.
you need to know that mod Z is basically distance from 0. Mod Z minus 1 is distance from 1 comma 0. Okay, so that is the
Yeah.
first one. Then we have second one is 1, 2, and 4.
Yeah.
Okay, so find the number of solutions of z cube plus z conjugate is equal to 0. Okay, 1 second, hold on, I'm getting a call.
Yeah.
Yeah, okay. So z cube plus z conjugate is 0, number of solutions, right?
Yeah.
So this one, you can do it in multiple ways. If you think of z as x plus iy, right? Then what you can say is z cube you can calculate easily.
Yeah.
So it will be x plus iy whole cube, and that will be x cube plus this cube, x cube. I cube will be minus I, right? So minus
Yeah.
I y cube plus 3xyi x plus iy, right? So this becomes x cube minus I y cube plus 3x square yi, and this becomes I square is minus 1, so minus 3xy square, right?
Yeah.
So this becomes x cube minus 3xy square plus I 3x square y minus y cube, right?
Yeah.
And z conjugate is simply x minus iy, right?
Hmm.
So z cube plus z conjugate, the equation becomes x cube minus 3xy square plus x plus I common 3x square y minus y cube minus y, right?
Yeah.
Equal to 0. So this boils down to two separate equations. Real part and imaginary part are both 0, right?
Okay. Yeah.
X cube plus x 1 minus 3y square is equal to 0. And another equation is minus y cube plus y 3x square minus 1 is equal to 0,
Yeah.
right? Okay, so this equation becomes y cube minus y 3x square minus 1 is equal to 0, which becomes y cube plus y 1 minus 3x square is equal to 0.
Yeah.
Both the equations look very similar.
Hmm.
1 minus 3y square is equal to 0. This and this. So you have to find number of pairs of x comma y for which this can be true, right?
Okay.
So 0 0 obviously fits.
Yeah.
0 0 obviously fits both the things. And if x is 0, then y can be anything. If y is 0, x can be anything. If x is 0,
But then the same X and Y
give me
are
a
there in
second.
both.
So if x is 0, y here can be anything, right?
Hmm.
But if x is 0, you put here, right?
Yeah.
Then y here can be y cube. Okay, so only y cube plus y, right, is equal to
Hmm.
0, right? So y into y square plus 1 is 0, right? So that is not possible, right?
Okay. Yeah.
So no point on the x-axis because that is not possible because x and y are supposed to be real, right?
Hmm. Yeah.
We have already taken the root 0 0.
Yeah.
Okay, so then how will we solve this?
So the
We
only
can
way to check is like trial and error.
no, I mean ideally you should think of something better. So add it. If you add
Okay.
it, I think we can take some common stuff.
Okay.
Uh, x cube plus y cube plus x plus y minus 3xy y plus x, right? See,
Yeah.
minus 3xy square and minus 3x square y. So you can take common.
Okay.
So I
Makes
will take
sense.
x
Yeah.
plus y common throughout. So 1 second.
Hmm. Okay.
If you take x plus y common throughout, you will get x square minus xy plus y square plus 1 minus 3xy, right?
Okay. Wait. I'll try it.
X plus y common throughout becomes, this one becomes x square minus xy plus y square
Yeah.
plus 1 minus 3xy.
Hmm.
So this becomes x square minus 4xy plus y square plus 1, right?
Hmm.
And x plus y is equal to 0. So either this is equal to 0, which will mean x is equal to minus y, or this is equal to 0.
Yeah.
This one is x minus y whole square plus 1 minus 2xy is equal to 0. So
Hmm.
doesn't help much. So I don't think this is the right approach to do this. So we have to think
Okay.
of something else. 0 0 is a root, and let's think of something else.
Okay.
Z cube plus Z conjugate is 0. So Z cube is equal to minus Z conjugate. Multiply by Z on both sides, right?
Hmm. Okay.
Becomes Z power 4 is equal to minus mod Z whole square, right? Z into
Yeah.
Z conjugate. So we are getting Z power 4 is completely real, is purely real, right?
Okay. Yeah.
And it's a negative number, right?
Hmm.
So Okay. Z power 4 is purely real, then Z will also be fourth root of that, right? Okay. So we can say uh, Z power 4 is negative. So
Yeah.
we can just say Z is equal to 1 by 2 and minus 1 to the power 1 by 4, no?
Wait.
Right?
Okay, yeah. You're fourth rooting both of them. Yeah.
Right. So this Z can be written as this will have four roots of minus 1,
Wait.
and
How?
you have not done nth roots of unity, no?
No.
Nth roots of 1 you have not done, so we will be studying that soon. So
Okay.
uh, you know that Z can be written as R E I theta, this you know.
Yeah.
So this equation is becoming where ei theta, e power I theta is cos theta plus I sin theta.
Hmm.
So this equation is becoming what? R cube ei 3 theta plus r ei minus theta, right? Because z
Okay, yeah.
conjugate will be what? Minus theta.
Yeah.
Z conjugate is r e power minus theta. So when you do that, you get r can be taken common. It becomes r square ei 3 theta plus e minus theta is equal to 0, right?
Yeah.
So r is not going to be 0 because we already know that z is equal to 0 is a root, so we can exclude that case.
Okay.
So you get r square ei 3 theta plus 1 by ei 3 theta is 0. Take denominator, this becomes r square ei 4 theta plus 1 is equal to 0, right?
Okay, yeah.
So actually this is what we were getting here. This is what we are getting. Z power 4 is minus mod z square, right? So you're getting r square ei 4 theta is equal to minus 1. So we have to figure out ei 4 theta. Okay, so minus 1. So minus 1 can be written as what? Ei pi, right? Think about it. Ei pi, right?
Okay, yeah.
Right. So actually, minus 1 can be written as ei 2k plus 1 pi. 2k plus 1 pi because 2k pi would have been 0. Ei 2k pi would have been plus 1, right?
Yeah.
Even multiple of 2 pi will be, even multiple of pi would be plus 1, and odd multiple of pi would be minus 1, right?
Yeah.
So if you write this way, here k can be anything, k can be any integer, right?
Yeah.
So now your r square into this is equal to minus 1. So what we will say is r square ei 4 theta is equal to e power I 2k plus 1 pi, right? So
So R should be plus or minus? Okay, not necessarily.
r, what r? This r,
No, no, I was thinking of something else.
ei 4 theta is 1 by r square uh, ei 2k plus 1 pi, right?
Yeah.
And we should get, if you take 1/4 power, right? So this will become ei theta should be equal to 1 by root r
Yeah.
ei 2k plus 1 pi by 4, right? So
Okay.
the problem is that r has to be plus or minus 1, no? Otherwise, how will it be? R has to be 1. It cannot be minus 1, so r has to be 1. Why?
Okay.
Because
Yeah.
this side it's a complex number with r square as the mod, right? And
Hmm.
this side is a complex number with 1 as a mod.
Yeah.
Any complex
Okay.
number
Yeah.
when it is written as e I theta, that's it, right? Then the 1 is the mod, no?
Yeah.
So
Okay.
they cannot be equal unless r is 1,
Okay. Yeah.
which we could have figured out from here also by noting that we could have figured this out here also by saying that z cube is equal to minus z conjugate. Take mods on both sides, right?
Hmm.
So mod z cube is equal to minus will go away, minus z, this is a mod z, right?
Yeah.
So you're getting mod z cube is mod z, can happen only for 0 or 1.
Okay.
So this part disappears, this part is gone, r has to be 1, right? Right.
Yeah.
So theta can be now 2k plus 1 pi by 4, right?
Hmm.
And k can be any integer, right?
Okay. Yeah.
So if you take k is equal to 0, you'll get pi by 4. K is equal to 1, you'll get 3 pi by 4, right? K is equal
Hmm.
to 2, you will get 5 pi by 4, and k is
Yeah.
equal to 3, you will get 7 pi by 4, right?
Hmm.
And if you do 4, you get 9 pi by 4, but 9 pi by 4 will become same as 2 pi by 4, right?
Okay. Yeah.
After that, it keeps repeating, no?
Hmm. Yeah.
You understand? 9 pi by 4 becomes pi by 4 only.
Yeah. Like after every 2 pi things.
Yeah, yeah.
Okay.
So basically, you're getting 4 roots here because theta values are becoming 4 different things, right?
Okay. Yeah.
R is equal to 1 and theta is equal to 4 different options, right? Pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4, right?
Yeah.
And the other
And
root
the
is 0.
zero. Yeah.
So total we are getting 5 roots.
Okay. Yeah.
5 roots we are getting. Here the idea here is what we have figured out is that you are taking REI theta form and figuring out the roots. So z cube plus z conjugate is equal to 0. First thing you can see that z is equal to 0 is the root.
Hmm.
Second thing you should notice is z cube is minus z conjugate. Take mods on both sides. So mod z cube is minus z conjugate mod, which is equal to z conjugate, which is equal to mod z, right?
Yeah.
So this equation implies that mod z is 1 or 0. 0 we have already taken. So mod z is 1, right?
Yeah.
If mod z is 1, then z can be written as simply ei theta, right?
Hmm.
You don't have to worry about the I part then, right?
Yeah.
Once you write that, it becomes ei3 theta plus ei minus theta is 0, right?
Hmm.
So this becomes ei4 theta plus 1 by ei theta is equal to 0.
Yeah.
And this part we have to solve to get how many possibilities are there. So ei4 theta is equal to minus 1, and this can be written as ei 2k plus 1 into pi,
Hmm.
and 4 theta must be 2k plus 1 into pi.
Yeah.
So theta can be 2k plus 1 pi by 4, and there are 4 possible values. So there are 4 roots of minus 1, right?
Yeah.
Like there are 4 angles of theta for which you can choose z as e power I theta, right?
Hmm.
And when
Yeah.
you raise it to 4th power, it will all give minus 1, right?
Okay.
So this idea we'll study in more detail. This is the nth roots of 1.
Hmm.
So
Okay. Yeah.
here you're doing 4th roots of minus 1, no, 4 roots of minus 1, right?
Yeah.
So we have found the roots actually. Ei pi by 4, ei 3 pi by 4, ei 5 pi by 4, and ei 7 pi by 4, right?
Hmm.
Check it once. Like ei pi by 4 is what number? Cos root 2 plus I by root 2, right?
Yeah.
Square it. If you square it, what happens? See, 1 by 2 plus I square by 2. So there's a minus 1 by 2 plus 2 I by root 2 into root 2 is 2 only, right?
Hmm.
So you get I when you square it, no?
Yeah.
So when you square that also, it will become I square, which is -1,
Okay. Yeah.
right? Similarly, same things will happen here also, and here
Yeah.
also, and here also. Okay.
Okay. Yeah. Got it.
So you're getting fourth roots of -1. So here 4 roots will come like that, and 1 root is 0. So 5 roots.
Yeah. I'll just check the answer. Yeah, it is 5.
Okay.
Yeah.
Then the next one is the second one.
Yeah.
If a is greater than 0, mod z is equal to a, find the real part of z minus a by z plus a, right?
Hmm.
So you need to know here that real part of any complex number is equal to z plus z conjugate by 2,
Okay. Yeah.
because z plus z conjugate by 2 would be real part, no?
Yeah.
You understand this, right?
Yeah. The imaginary parts will cancel out and then.
So we just have to do z minus a by z plus a plus z minus a by z plus a whole conjugate, right? And half
Hmm.
of that, right?
Oh, okay.
So this whole conjugate, how will you split it? That we can do this by this, right?
Hmm.
And that will become z conjugate minus a is real, right?
Yeah.
A is real is given. So minus a by z conjugate plus a, right?
Yeah.
So now we'll add z minus a by z plus a plus z conjugate minus a by z conjugate plus a, right?
Yeah.
This becomes z plus a, z conjugate plus a, and multiply this. Z into z conjugate is mod z square
Hmm. Yeah.
minus a z conjugate plus a z minus a square plus z conjugate square minus a z plus a z conjugate minus a square, right? So this minus
Hmm.
az, this cancels, this cancels, this cancels, right?
Okay. Yeah.
On top, you are getting what? 2z square minus 2a square, right?
Yeah.
But mod z is a, right?
Okay. Yeah.
So 2a square, right? Minus
Hmm.
2a square. So 0,
Okay.
right?
0.
So real
Okay. Yeah.
part of this is 0,
Oh, okay. Yeah. Got it.
right? So you just need to use this and use properties of conjugate and all. And the most
Yeah.
important property is this.
Yeah.
Okay. Uh,
Okay. Got it.
then it's fourth one.
Yeah.
Okay. Fourth one is minus pi is less than arg z is less than minus pi by 2. Okay. Find argument of z conjugate minus argument of minus z conjugate, right?
Hmm.
So here you have to understand what is the meaning of the argument, right?
Yeah.
So the argument and the definition is that argument is the z is equal to r e I theta. Theta is the argument. Okay.
Yeah.
However, since argument can be many valued, no. So for example, this angle is theta. If you write it like this is r and this is theta, right?
Hmm.
And you generally go in a clockwise manner like this, right?
Yeah.
But the problem is that you can come back to this point again, right? And you can
Hmm.
have a different angle, right?
Yeah.
So the way we write argument in principal value of the argument, we write in such a way that we measure angles from 0 to pi till here, and
Yeah.
then this side we measure it from till minus pi.
Okay.
So when you write argument of z, you are going to write it while it satisfies these conditions.
Okay.
So basically measure angles as long as complex number is in first quadrant or second quadrant, you will start measuring from this side, right?
Yeah.
And you will go up from 0 to 180 degree. But
Hmm.
if your complex number is in third quadrant or fourth quadrant, you will actually specify the angles from this side and you
Okay.
will call it minus of that angle, right?
Yeah.
So if it is here, I would have called it minus 135 rather than plus 200 something, right? 50.
Yeah.
Okay.
Yeah,
So
got it.
you always keep your arguments in this range. So here what he has said is argument of z is between minus pi by 2 to minus pi, right?
Hmm.
So it is in the third quadrant here, no?
Okay, yeah.
Because minus pi by 2, when you measure, you're measuring from this side, right?
Hmm.
So the complex number is in the third quadrant. Okay.
Okay.
So 1 second. Complex number z is in the third quadrant. We know that. So let's say z is somewhere here, right?
Yeah.
So z is there, then z conjugate will be where? Z conjugate will be here, right?
Okay. Yeah.
Right? Reflection on the x-axis, correct?
Yeah.
So this angle is the argument of z, right?
Hmm.
This angle is argument of z, and this angle's value is minus something, right? Minus
Yeah.
90 plus something, right?
Yeah.
So for example, take some easy angle. Let's say this is 120, right?
Hmm.
Let
Okay.
argument of z be 120. So I'll be minus 2 pi by 3 is my argument of z, right? That fits this condition.
Yeah.
So if this is 2 pi by 3, then this is 2 pi by 3, right?
Yeah.
So argument of z conjugate is becoming what? 2 pi by 3, because it is in second quadrant, we have to measure it from this side, right?
Okay. Yeah.
Right. So this is becoming 2 pi by 3 and minus argument of minus z, right? So this is my z conjugate, right? And this is my z, right?
Yeah.
So minus z is a reflection about the origin, no?
Okay. Yeah.
No, minus z conjugate. So minus z conjugate was here, no? So reflection about the origin would be here,
Okay. And the fourth one.
right?
Yeah.
So this is minus z conjugate, right?
Hmm.
So this angle is 60, right? Then because
Yeah.
this is 60, this is 60, right?
Hmm.
So 60 comes by doing pi minus argument of z, right?
Hmm.
Because argument of z was 2 pi by 3 here, right? For us.
Okay. Yeah.
60 will come by basically doing pi minus argument of z, right?
Yeah.
So here this would have been 2 pi by 3 minus argument of minus z is pi by 3. Actually, not pi by 3, minus pi by 3, right?
Hmm.
Minus z, this is minus 60, no argument.
Yeah. But isn't argument of z conjugate? Okay. Yeah. That is plus 120. Yeah. My bad.
Argument of z conjugate was plus 120.
Yeah. Plus
Argument of
120.
minus z conjugate is minus 60, right?
Yeah.
So answer should be pi, right?
Yeah.
Okay.
Okay.
So think about what is happening. Argument of z conjugate here becomes negative of argument of z, right?
Hmm.
And argument of minus z, right? Minus z conjugate, right?
Yeah.
Is becoming pi minus argument of z, but negative of that, right?
Yeah.
Minus of pi minus argument of z, right?
Yeah.
No, pi plus argument of z, because argument of z itself is negative, right?
Oh, okay. Yeah.
You remember it was minus 2 pi by 3, no? So it
Hmm.
became
Okay.
60
Minus.
if you do plus, right?
Yeah. Okay. Got it.
So the answer will come out to be pi regardless.
Oh, okay.
Plus pi minus of this, minus minus becomes plus, and argument z cancels, right?
Hmm. Okay.
See, it'll be easy if you think of it in terms of like which quadrant is it and how do I
Yeah.
measure my arguments, right?
Okay.
So if it is in third quadrant, I have to measure it from this side, and angle will be minus 120. So this has to be some minus 120. When you do conjugate of that, this will be plus 120. So this answer is
Yeah.
plus 120. And when you do negative of a complex number, it is reflection of that about the origin, right?
Okay.
So this has to be this angle. Again, you measure it from this side because it is in fourth quadrant, right?
Yeah.
So this angle has to be minus 60, right? So
Hmm.
minus 60 here, and minus minus 60 becomes plus 60. So 120 plus 60, 180 is the answer.
Yeah. Okay. Got it.
Okay. So don't try to memorize this ever. Like they might give you in the book, they might give you argument of z is some minus theta, minus pi plus rz, if it is in third quadrant, if it is in fourth
Yeah,
quadrant.
yeah, they did give that.
Don't try to memorize that, because that is
Okay.
sure short chance of making mistakes then.
Hmm.
Like, think about it, that if it is in first and second quadrant, you have to measure angles like this, so it will go up from 0 to pi. And
Yeah.
if it is in this quadrant, you have to measure like this, and you have to write it with minus angle, right?
Hmm.
After that, whatever comes, you can figure it out if you
Yeah.
understand that much, right?
Okay.
So your point is in fourth quadrant, then if you have to do conjugate, put it there. If you have to do
Hmm.
reflection, put it here. Minus z, put it there, or minus z conjugate would be here, right?
Yeah.
You understand, if I take z and make minus z, it has to be, both x and y have to be reversed, right?
Hmm. Yeah.
It's a
Okay.
reflection about the origin. So if it was z conjugate here, then my minus z conjugate has to be here.
Yeah.
So after that, it is easy to figure out, take a specific angle and you will know what to do.
Okay. Yeah.
Take a easy angle like we did 120, right?
Hmm.
Which fits the conditions of the problem, and then you can figure out what will be happen.
Okay.
Okay. Then
Yeah.
the next one is which one? 5, illustration. No, illustration 18.
Yeah.
Okay. You are given mod of z minus 4 by z is equal to 2. Then find the greatest value of mod z, right?
Hmm.
Greatest value of mod z. Mod z. Okay. So what he's saying here is he will use the triangle inequality. So mod z is equal to mod of z minus 4 by z plus 4 by z, right?
Hmm.
This is equal. This is the same thing, right?
Yeah.
But we know that mod of a plus b will be less than equal to mod of a plus mod of b.
Yeah.
Why is that true? Because you can think of this in terms of um, just think of it in terms of two complex numbers. If you add, you will get, it's like a vector, no? A vector and b vector. This
Hmm.
is your a plus b vector, right?
Yeah.
So this is one complex number, this is another complex number, and this adds up to be this. So this mod will always be less than the direct addition like this, no?
Yeah. Okay.
A resultant of two vectors will have a cos theta component, no?
Yeah, and that's always
A
assumed.
square plus b square plus 2ab cos theta root, right?
Yeah.
This is the resultant of two normal vectors, and this is simply a plus b. So they
Okay.
will be equal only when cos theta is 0. But
Okay.
otherwise, this will be less, right?
Yeah.
So he will say that this thing will be less than equal to mod of z minus 4 by z plus mod of 4 by z, right?
Hmm.
So now you're getting less than equal to, this is given to be 2. 2 plus 4
Okay.
by z, right? So you get
Yeah.
mod of z is less than equal to this, right?
Hmm.
So now this becomes a quadratic equation, because you can now simply convert this inequality into a simple quadratic type of inequality, where z minus 4 by mod z is less than equal to 2. So mod of z whole square minus 4 by mod of z is less than equal to 2. Therefore, mod of z whole square minus 4 is less than equal to 2 mod z. Mod of z
Hmm.
square minus 2 mod z minus 4 is less than equal to 0. And this
Okay. Yeah.
this quadratic equation inequality can be solved easily, because you can do this perfect square, plus 1 minus 5, right? So you have
Hmm.
mod of z minus 1 whole square is less than equal to 5, right?
Okay.
So
Yeah.
mod of z minus 1 will be between the range of minus root 5 to root 5, correct?
Okay. Yeah.
So mod of z will always be less than root 5 plus 1.
Hmm.
This is the maximum value of mod of z. If you get this quadratic inequality, you can solve it, no?
Yeah.
You can also try
Okay.
to
I
do
got it.
it by plotting the graph. So this quadratic inequality looks like this, right? because the graph faces upward, no?
Yeah.
For what I mean to say is, if you have mod z square minus 2 mod z plus, what was it? Plus 4, no,
It
minus
was -4.
minus 4, right?
Yeah.
Is less than equal to 0. So think of mod z as your x. So this is like x square minus 2x minus 4 is less than equal to 0. If you plot the
Hmm.
graph of this, when the first coefficient is positive, the graph opens upward, right?
Yeah.
And this graph has two roots because b square minus 4ac is positive.
Hmm.
So there, this is the situation, right? This is the graph of this function, right?
Yeah.
Now, if it will be less than 0 only in this interval, no?
Hmm.
So clearly, x has to lie between the two roots, right?
Yeah.
X has to lie between the two roots. So the higher root will be the maximum value of x, and the lower root will be the minimum value of x, which will satisfy this equation, right?
Yeah.
Inequality.
Okay.
So we are just finding that root, right? If you find root of this, it will be 2 plus minus root of b square 4 minus minus plus 4. So 20 by 2, right?
Hmm.
So this will be 1 plus root 5 minus root 5, right? So this
Yeah.
point is 1 minus root 5, this point is 1 plus root 5. So x
Okay.
has to lie between that range for the quadratic to be negative, no?
Yeah. Okay.
You
Got it.
understand?
Yeah.
Uh, then, then there is, among the complex numbers which satisfy this, find the complex number which have a, b, c, d. Okay, okay. So first of all, complex number z which satisfy mod of z minus 25i is less than equal to 15. So find the complex numbers which has least positive argument. Least positive argument. So first of all, you have to identify what this means. And whenever you have a situation like this, z minus a is equal to b, right? That
Yeah.
means the complex number z is such that its distance from this a point is equal to b, right?
Okay.
So it is at an equal distance b from the a point. So this is the locus of a circle, locus of a circle with center a and radius b.
Oh yeah.
With center a and radius b, right?
Yeah.
Here a could be a complex number, a could be a real number, no matter what it is. It could be z minus 1 is equal to 2. Here center is 1 comma 0, radius is 2.
Hmm.
Here it is 25i, so center is 0 comma 25i, and
Okay.
or 0 comma 25 because I axis is y axis, right?
Okay. Yeah.
And
That's
radius is 15,
yeah.
correct? So if it was z minus 1 minus 2i is less than 2, then center is 1 plus 2i, or basically point 1 comma 2, right?
Okay. Yeah.
And radius would have been 2. So
Yeah.
equality case is that if it was a less than equal to, that means it is inside that circle because the distance is less than the radius.
Hmm.
So it is interior of a circle, all the points
Okay.
inside the circle.
Yeah.
So if you do the graph of this, it will become 0 comma 25 is the center and the circle of radius 15. So this point will be 0 comma 10 and there is a
Hmm.
circle, and this point will be 15 comma 25, right?
Yeah.
And this point and all you can draw like this, right?
Hmm.
This is my circle, this point is minus 15 comma 25,
Yeah.
right? And
Yeah.
this is my circle, 0 comma 10 is this point. Now all the points inside the circle are satisfying the equation z minus 25i mod is less than 15, less than equal to, right?
Yeah. Yeah.
Now you have to find the complex numbers that satisfy this locus and have least positive argument, right?
Yeah.
Least positive argument. So that means the lowest positive angle, right? Positive angles are measured in this side, right? So if I draw
Yeah.
a line like this, right?
Yeah.
If I draw a line like this, then that line will be the lowest possible tangent line, right?
Okay.
Correct.
Yeah.
So let's think about what he's saying is complex number having least positive argument and maximum positive argument in this case are points of contacts from tangents drawn from the origin to the circle, right?
Yeah.
So why is he saying that? Uh, Tangents drawn from origin to the circle. Why is he saying that? Because positive argument of a complex number here, right?
Hmm.
Some complex number here, argument would have been, you would have joined it to the origin and you would have found the tan theta or y by x, right?
Yeah.
Tan theta would have been this y coordinate of it and x coordinate of it, right? For this point
Hmm.
x comma y. Now, the lowest angle possible will be when you can reach the farthest possible x possible, no? You
Okay.
understand? Tan theta is equal to y by x, no?
Hmm.
For the argument. If x
Okay.
is
Yeah.
big, then the angle is small, no?
Okay. Yeah. Got it.
So if you can draw a tangent from say 0 till 15, this point 15 comma 25, right?
Hmm.
Then you will get the least positive argument, right?
Yeah. Okay. Got it.
But it may or may not be possible uh, that the tangent is at 15. It might be unlikely
Oh
that it
yeah.
is at 15, right? It could
Yeah.
be at some other point, no?
Hmm.
So
Okay.
whatever is the tangent from the origin to the circle, the point where it touches will have lowest, no?
Okay. Yeah.
Not necessary that it will be at 15, right?
Yeah.
So so let's find out this possible angle, right? And the same thing applies here also.
Hmm.
The biggest possible tangent angle, right?
Yeah.
So okay, so this is a circles question now. From 0, 0, you have to draw tangents to this circle, right?
Okay. Yeah.
So any line through 0, 0 will be y is equal to mx, right?
Hmm.
And circle equation is obvious, already known to you, right?
Yeah.
So this is going to be radius, right? 15.
Yeah. 50.
And this distance is going to be 25, right? Correct? Because the
Wait.
point was 0 comma 25,
Okay. Yeah.
right?
Yeah.
And so if this angle is already known, no, phi, tan sine phi is going to be 15 by 25, this angle
Yeah.
15 by 25, right?
Yeah.
So if this angle is known, this 90 minus phi is this angle, right?
Yeah. Okay.
Tan
Yeah.
phi is no, sine phi is 15 by 25, so sine phi is equal to 3 by 5, right? So
Hmm.
phi is basically equal to 37 degree, right?
Yeah.
So this is 37 degree, this is 53 degrees.
Yeah.
That is the least possible angle. By
Okay.
symmetry, this will also be 53. So this total angle will be, this is the argument of this side complex number, no?
Hmm.
180 minus 53, so 127 degrees,
Yeah.
right?
Okay.
And here it is 53 degrees for this one, right?
Hmm. Okay.
Then,
Yeah.
then, so we didn't have to do coordinate geometry, you can do by simple geometry only. Then
Hmm.
least modulus and maximum modulus, right?
Yeah.
Least modulus means shortest distance from 0, right? That is
Okay.
obviously this 0 comma 10, right?
Okay. Yeah.
And maximum modulus is longest distance from 0, 0, right?
Yeah.
That should be
So
this
plus
point, right?
30.
0 comma 40,
Yeah.
right?
Okay. So just 10.
This 40, I don't think any point will be farther than that.
Yeah.
This will be 40 and this will be 0 comma 10,
Okay.
right?
Yeah.
What else is there?
Yeah,
Is
those
there
are my
any?
doubts.
Okay. Then uh, what we will do is we'll discuss whatever topics has not been covered and whatever is a problem. So
Yeah.
the thing we'll discuss is representation of complex numbers in Euler or polar form, and geometrical meaning, geometrical meaning, rotation, okay, and rotation, and nth roots of 1.
Okay.
Just hold on, I have to take a call, okay?
Yeah.
I'll be back in 4-5 minutes.
Okay.
Hello. Okay.
Yeah.
So what we'll first be looking at is complex numbers and how they can be represented in different forms.
Yeah.
1 second. Yeah. So see, complex numbers, you have learned that it can be represented like this, right? Z is equal to x plus iy, right?
Yeah.
Here, basically in your two-dimensional plane, every point on the plane is a complex number. Okay.
Yeah.
So this is x comma y, right?
Yeah.
And any other point like x and y can be positive, negative, right? So all four quadrants will be covered, right?
Yeah.
If you think about real numbers were not having this pair, right? There was just one number, right? So
Yeah.
real numbers are actually, this line is the real line, x-axis, right?
Yeah.
So that's why real numbers are sort of one dimensional in that sense, right? It's only on this line. Every number can be put on this line.
Okay. Yeah.
Right? However, complex numbers have added an extra dimension in y also, right? So you can
Yeah.
cover everything in the plane using complex numbers, right?
Yeah.
So if we define some new number which has a triple, right, then that would cover 3D space, right?
Okay. Yeah.
So if you want, you could have defined a new number called xyz that will represent everything in 3D space, right? Actually, there are numbers called quaternions, which are 4D in nature. Like, so you'll have x, y, z, w, right? So mathematicians have figured out ways to define and use numbers which are more dimensions than two also, right?
Okay.
So complex number is just second dimensional type of numbers. Real numbers are unidimensional, and there could be higher types of numbers also possible. So here, this for complex numbers, xy is one way to represent it. However, you can also write it in terms of this distance and this angle, right? Which is where you get the Euler form, right? R e I theta, because this becomes r cos theta comma r sin theta, right? X and y.
Yeah.
So because this distance is r cos theta and this distance is r sin theta, you can
Yeah.
write x plus iy as r cos theta plus I r sin theta, and you can say r cos theta plus I sin theta, right? And
Yeah.
that becomes r e I theta. And this is because of Euler's formula and his theorem, which was saying that e power I theta is equal to cos theta plus I sin theta. Now, the proof of this can be done. However, it involves some infinite series. So actually, we might cover it when we do it in calculus, but what you should know is that sine theta is basically this series. You have not seen this, right?
No.
Sine theta is actually this series. Do you know the meaning of factorials?
Yeah.
Factorials, you know, right?
Yeah.
Okay. So cos theta is this series, 1 minus theta square by 2 factorial plus theta power 4 by 4 factorial, and so on. And e power x is basically 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, and so on.
Okay.
So all of these are infinite series whose values give us the value of sine theta, cos theta, and e power x. Now, how does this e power I theta become this? Uh, it will be clear if you just do the expansion. So for example, let's see, e power I theta is equal to 1 plus I theta by 1 factorial plus I theta whole square by 2 factorial plus I theta whole cube by 3 factorial and so on, right?
Yeah.
So if you notice, this becomes 1, I square will be minus 1, no?
Hmm.
1 minus theta square by 2 factorial, then I power 4 will be plus 1, right?
Yeah.
So plus theta power 4 by 4 factorial. These are all real parts, right?
Okay. Yeah.
And this will have an I, this will also have an I, right? I common,
I get
this
it.
will become theta by 1 factorial. This will be I cube is minus I, so this will become minus theta cube by 3 factorial, right?
Yeah.
And there will be plus theta 5 by 5 factorial afterwards, and so on. Now you
Okay.
notice that this is what I had written as cos theta,
Yeah.
and this is what was the series for sine theta. So
Yeah.
from there, he got that cos theta plus I sine theta. Okay,
Okay.
e power I theta. So obviously, you need to know why cos theta is this or why sine theta is this. That comes from Taylor series, Taylor series, and Maclaurin series. That is something that will be studied when we do calculus.
Okay.
However, you can convince yourself that that is true by taking some angles. So sine theta is equal to theta by 1 factorial minus theta cube by 3 factorial plus theta 5 by 5 factorial and so on, right? And here all the angles are expressed in radians. Okay, so let's take some values, and let's take, we know sine pi by 3 is equal to root 3 by 2, right?
Yeah.
Right, so let's check whether pi by 3, if I take this series, is giving me root 3 by 2, right? So to put pi by 3 in this, so it is pi by 3 by 1 factorial minus pi by 3 whole cube by 3 factorial plus pi by 3 whole 5 by 5 factorial and so on till infinity. However, the series will quickly converge in the sense that afterwards these values will not matter so much because the division is a huge division.
Yeah.
You understand? There's 3 part 5 and 5 factorial, no, denominator.
Yeah.
So that is very big number. So this value, and also you can ignore this parts.
Okay.
So more or less the first two terms will decide the value, right?
Okay.
So what is pi by 3 is, first term is simply pi by 3 minus pi cube by 3 cube is 27 into 6, right? Right. So pi is 3.14, let's say. 3.14 by 3 will be almost 1.05, right?
Yeah.
Minus pi cube. Pi cube, pi square is almost 10. Pi square is 10, and 10 into pi is 31.4.
Yep.
31.4 by 27 into 6, right? So 31.4 divided by 27, 6 are 162, right?
Okay.
Correct. 162, no? Yeah. Yeah. 162. So this is 30. Let's take it as 32 by 162 for convenience. 32 by 160, let's take for convenience.
Yeah.
So this will be 2 by 10, right? So 0.2, right?
Okay.
So what is the subtraction? It becomes 0.85.
Hmm.
And what is this? 1.732 by 2, right?
Oh, yeah.
So not exact calculations, but you will find that it will match. Okay. So actually, people discovered the series for sine and cos very early. In 1600s, only people discovered this.
Oh.
Okay. So then they were able to fill up the sine cos tables very easily, right?
Yeah.
So now any possible value of sine you can actually find. Like even if it is some arbitrary angle, somebody gave you 27 degree, right?
Yeah.
You can convert it to radian and put it in the formula and use first 2-3 terms only, it will give the answer.
Oh, yeah.
Right?
Yeah.
So sine and cos are these series, and it comes from Taylor series. So when we do calculus, we'll revisit this. Actually, you can write such series expansions for many functions. Like for tan, for whatever function you care about. Most of the normal continuous and differentiable functions you can write series like this.
Okay.
However, this is anyway a digression. What we need to know is this complex number, which was r cos theta comma r sin theta, can be now written as r e I theta, right?
Hmm.
Because e I theta is equal to cos theta plus I sin theta, right?
Yeah.
So that is true. Then now we have a nice way of representing multiplication of complex numbers. Because if you have z1 is equal to r1 e I theta 1 and z2 is equal to r2 e I theta 2, multiplication becomes very easy, right?
Hmm.
So simply r1 r2 e power I theta 1 plus theta 2, right?
Yeah.
And you can see that multiplication is a rotation because if you had two angles, this was theta 1, this was theta 2, and two complex numbers, right? Z1 and
Hmm.
Z2, right?
Yeah.
So notice that when you multiply the final complex number, this is a real part, right?
Yeah.
And this is the angle that it makes, right?
Hmm.
So final
Okay. Yeah.
complex number will be at an angle which is the addition of the two angles, no?
Yeah.
So you're sort of rotating Z1 by Z2's argument, right? And getting
Okay. Yeah.
to this point Z, right?
Yeah.
Right? This angle is theta 1 plus theta 2 here, right?
Yeah.
So complex number multiplication and division becomes rotation, right?
Hmm.
It is actually rotation plus scaling. By scaling, I mean the R value is changing, no?
Yeah.
So what was the meaning of the R value? Meaning of R was the distance from origin to the complex number, right?
Hmm.
Now here it was R1, here it was R2. But in this combined thing, it is product of the two, right?
Yeah.
R1, R2. So the whole complex number has gotten stretched by some amount, right? It is longer,
Hmm.
that line, right?
Yeah.
So if I take, say, first complex number was 1 EI pi by 6, and second complex number was 2 EI pi by 3, right?
Hmm.
So final complex number should be 2 EI pi by 6 plus pi by 3, which is equal to 90, right?
Yeah.
2
So
EI
doing.
pi by 2, right?
Yeah.
Which is simply 2I, right? Because EI
Okay.
pi
Yeah.
by 2 is equal to I,
Okay.
right? So in this case, actually I made a mistake. I should not have increased the length of this, right? Because the length did not increase now.
Oh yeah. It's the same.
It is the same 2 length, right?
Hmm.
2 into 1. So in this case, because you are multiplying with r is equal to 1, the length of this vector, this complex number did not change and it became same length, right?
Yeah.
However, if this was 3 EI pi by 6, then the final complex number has length
Yeah. It
6,
becomes
right?
6. Yeah.
So it is rotation plus scaling. Scaling means stretching or compressing, right?
Hmm.
If one of your r's was less than 1, then the final one will be shorter, right?
Yeah.
Than the second one, right?
Yeah.
So division is obviously again r1 by r2 ei theta 1 minus theta 2, right?
Hmm.
So division is rotation in the clockwise sense. You are reducing the argument of one of them, right? By the
Yeah.
second one's argument, right?
Hmm.
Are you understanding?
Yeah. Got it.
So division is clockwise rotation and this is anti-clockwise rotation, right? In
Yeah.
multiplication argument increases, in division argument decreases, right?
Yeah.
Now also in division, you are also doing some scaling, right? Your R value is changing, correct?
Hmm.
It is becoming R1 by R2.
Yeah.
Okay, so this is important because when we do geometry, what we need to understand is angles, right?
Hmm.
So we need to figure out these angle stuff when we do geometry. So right now we'll just focus on some properties of this Z, in the sense that Z, R, E, I, theta, we want to understand each component, mod and argument. So
Hmm.
mod Z is called R. Mod Z is basically just simply root over x square plus y square, right?
Yeah.
And that is equal to R. So some properties of mod you would have seen properties like Z conjugate is equal to mod Z square.
Yeah.
Z1, Z2, if you take whole mod, you will get Z1 mod. No, this is conjugate. If you take whole mod of Z1, Z2, right? It will be mod Z1 into mod Z2, right?
Yeah.
And similarly, mod of Z1 by Z2, if you take, it will be mod Z1 by mod Z2, right?
Yeah.
So there are some properties that you can easily verify. If you want to verify all of these properties fast, you should use this.
Okay.
Euler form will be the fastest way to verify. Otherwise, you'll have to actually do x plus iy into x minus iy. Okay,
Oh yeah.
that will be annoying. So, the most important lesson here is that the x plus iy thing, right? That is not a very convenient way to do complex numbers. Not a very convenient tool in
Yeah.
the sense because many operations are quite hard in x plus iy. Addition and subtraction is easy, but everything more complicated than that is harder there.
Yeah.
Yeah. So mostly you will be using Euler form or polar form,
Okay.
REI theta. So think of questions using this more rather than this. They might be teaching you in Allen to put x plus iy everywhere. Don't do that.
Okay. Yeah.
Okay. Don't do that blindly. Like many people just keep doing x plus iy and then they keep getting confused.
Yeah.
Okay. So this is more important and valuable than this. If nothing is working, you can try this, but it is unlikely that if everything else here is failing, that this will be very nice.
Yeah.
You understand?
Yeah.
So okay, this is one thing. Then argument. So argument we had discussed while solving. So argument is the theta angle that comes, right? Theta angle that comes in the complex number, right? And argument are measured from this side generally. But
Yeah.
because you can go in a full rotation and come back to this point, right? Argument is always multi-valued, right?
Yeah.
The same complex number could be said to be having argument of 60 or it can 420, right?
Yeah.
2 pi plus 60 is also valid, right?
Yeah.
So when we talk about argument, generally we refer to it as the principal value of the argument. Principal value of the argument is only one value of the argument, which we will be using mostly. And there I explained earlier that it will be always measured from like this. You will always specify it between minus pi to pi.
Yeah.
Okay. So for first and second quadrant, you will measure it from this side and go up till 180. And if the
Yeah.
point is in the third or fourth quadrant, right, you will measure it from this side and go from minus 1 degree to minus 179 degree and stuff,
Yeah.
right? So it will not equal minus pi because plus pi is already taken, right? So this point is
Okay. Yeah.
already used up, right?
Yeah.
So there is a equality sign here, but no equality sign here.
Yeah.
Right? So this already covers the entire 2 pi plane, right? So you have to put these arguments using these rules, right?
Okay.
Now,
Yeah.
obviously, there will be some properties here. Argument of Z1, Z2 will be equal to argument of Z1 plus Z2, right?
Yeah.
Now, this property can be verified very easily because you can just do Euler form again and you can see
Yeah.
product of
Theta 1 plus
this
theta
is
2.
theta 1 plus theta 2, no?
Yeah.
So argument of that complex number, which is R1, R2, e power I, argument of this complex number is simply theta 1 plus theta 2, which is arc Z1 plus arc Z2, right?
Yeah.
However, sometimes you have to be careful in these results. There will be results like this is equal to arc Z1 minus arc Z2. And there will be also results like this. Arc of Z power n is equal to n power n times arc Z, right?
Yeah.
These results are obvious if you use Euler form, see? Because this will be R1 by R2 e power I theta 1 minus theta 2, right?
Yeah.
So it will become argument of that is theta 1 minus theta 2, right?
Yeah.
So that is why this result comes. And similarly, Z power n will be R power n e power I n theta, right?
Yeah.
So argument of that is simply n theta. So it is n times arc Z, right?
Yeah.
However, you have to be careful sometimes because what happens is when you do argument of this and when you add these arguments, right? After addition, it could exceed 180 degree, right?
Oh yeah.
Like if I had one which was 60 and one which was 130, right? So you can write 130 plus 60, but the answer will come 190, right?
Oh, yeah.
And this answer should not have been 190, right? Because if you are referring to principal arguments, you will write it like this, right? If
Yeah.
your angle is beyond 190, you should write it as this way, right?
Yeah.
You understand?
Yeah, I got it.
So there will be a plus minus 2n pi here in everyone.
Okay.
Plus minus pi or something, right? Plus minus pi, because once you do the calculation here, it depends on where that final answer is, right? Which quadrant.
Yeah.
If suppose n times you added this argument of 30, right? 5 times you added, then 150 is correct, right?
Yeah.
But if you added 7 times, then it should be not 210. You cannot write it as 210, right? Makes sense. If
Yeah.
it became 210, you have to specify it as minus 150, right?
Yeah.
So basically, the only thing you have to be careful in this is the final answer that comes still satisfying this condition or not, right?
Okay.
If
Yeah.
the final answer does not satisfy this condition, then check which one it should be, right? Which side is it coming, right?
Yeah.
And take the appropriate minus pi or whatever, right?
Okay. Yeah.
So again, there will be some rules and all they will give in the Allen book, right? Where they will show plus n pi or minus n pi in that case and all. Don't memorize anything.
Okay.
You would have seen this argument properties. There will be a list of properties, okay?
Yeah.
And then there will be a plus n pi and stuff added at the end. Can you just check it now once again?
Yeah. I'll check.
Properties of argument section.
Okay. Yeah, they just gave plus 2k pi and k is an integer, like after all those three.
Everywhere they put plus 2k pi.
Yeah.
Did they put a minus k pi or something somewhere? No.
No, just these
Plus
three.
2k pi and all, but they did not explain why is that plus 2k pi is coming, right?
I mean, they said RHS should lie between minus pi and pi, but they didn't like tell why. So
Yeah.
they
So
just
minus
gave
pi
that.
and pi, they should. So don't use those formulas without understanding. So basically, the idea is that this complex numbers argument also you will express in principal value form, right?
Yeah.
You will not want it to be some 210 suddenly, because everywhere you are following this rule for argument, right?
Yeah.
So adjust it accordingly if the answer is coming beyond that range, right?
Yeah.
Then argument and this is done. Then we come to the geometrical part, where first thing that you need to know is to do geometry. If you recall in 9th, 6th, 7th, 8th, whatever you have learned, the first thing that you learned was distance.
Yeah.
Distance, and the second thing is angles. Like in geometry, we measure lengths, we measure angles, right?
Yeah.
So similarly, here also, using complex numbers, you can measure lengths, you can measure angles, okay? So once we can measure angles and lengths using complex numbers, then every result in geometry you can replicate using complex numbers.
Okay.
So for example, so if I want to measure distance, so I know Z is here, distance from origin is called mod Z, right? And if my Z1 is here, right, and Z2 is here, right?
Yeah.
This distance will be mod of Z1 minus Z2, right? This distance. Why is that true?
Okay.
Because think of this as this Z1 as a vector till here, right? Z1 is Z1 is x1 plus iy1, no?
Yeah.
Or x1 comma i1 y1 point, right? Z2 is what point? X2 comma y2, or you can think of it as x2 plus iy2, right? Now the same logic of complex numbers can be extended to vectors also. You can say I can write a position vector from origin to Z1, right? What will be the vector for that? It will be x1 I cap plus y1 j cap, right?
Yeah.
This is the Z1 vector, right? And what is the Z2 vector? Z2 vector is simply x2 I cap plus y2 j cap, right? So if I have Z1 vector and Z2 vector, then obviously this third vector I can figure out by addition rule of vectors. You can say that this vector plus this vector should be this vector, right?
Yeah.
So
Okay.
what is the third vector? Third vector, so I will write z1 vector plus unknown vector, right, is equal to z2 vector, right? So third vector is simply z2 vector minus z1 vector, right?
Yeah.
So third vector is becoming what? x2 minus x1 I plus y2 minus y1 z j, right? So length of that third vector is what? Length of that third vector is root over x2 minus x1 square plus y2 minus y1 square, right?
Yeah.
y2 minus y1 square. So that is clearly mod of this, right?
Yeah.
So basically what we know is complex numbers can also be represented as vectors where each complex number is a position vector from the origin, okay?
Yeah.
So this is a position vector from z origin, which is z1. This is a position vector from origin, which is z2, right? So this third vector is clearly going to be z1 or z2 minus z1, right?
Yeah.
Third vector, right? So if this third vector is z2 minus z1, its modulus is going to be the length of that vector or the distance between those 2 points, right? Correct?
Yeah, got it.
So distance between those 2 points. So if now you know the meaning of this means distance between 2 points, then sort of like you have understood how to represent any distance, right? Uh, that is why z minus 0 was mod z, which is distance from origin, right?
Yeah.
Correct. And any triangle or any figure that you have, you can always write all the distances now, right? So simply, if you have a triangle like this, z1 is this vector, z2 is this vector, z3 is this vector. This distance is z3 minus z1 mod. This
Yeah.
distance is z2 minus z3 mod, right? Here,
Yeah.
when you are taking distances, the order doesn't matter. But when you are writing the complex number, the order matters, okay?
Okay.
In the sense that if I am writing this vector, right, then obviously I should write z3 minus z2, right?
Yeah.
If I'm writing this vector, I should write z3 minus z1. If I'm writing this vector, I should write z1 minus z2, right?
Yeah.
If you write arrows differently, the vector order will matter, right?
Yeah.
However, distance, it doesn't matter, right? So this is fine, this is fine, this is fine, right?
Yeah.
So distances are sorted. This is how we did that question, the question where mod z was less than z minus 1, right?
Yeah.
So we said mod z was less than equal to mod z minus 1. Now z minus 1 means distance between z and distance between 1. Where is 1? 1 is on the real axis here.
Yeah.
And z is anywhere it can be in space, right? In the 2D space, z can be anywhere. However, you have to satisfy this condition also, that mod z is distance from origin, right?
Yeah.
And this is distance from this. So what we have to ensure is that this distance is less than this distance, right?
Yeah.
The distances will be equal if you are on the perpendicular bisector. Every point to this side will have this distance less than this distance, right? That's why we got half plane this side, right?
Yeah.
Okay. So distances
Okay.
will be fine. Suppose it's a square, right? We will know that this z1, z2 should be equal to z3, z4, right?
Yeah.
Mod z1 minus z2 is equal to mod z3 minus z4. To simplify this result further, if something else is required beyond this, you should do basically this, and then use the property that you can write z1 minus z2 into z1 minus z2 conjugate here, right?
Okay.
And similarly z3 minus z4 conjugate here, right? And then split the conjugate and multiply it out and get a new result, right?
Yeah. Sir, are you talking? I can't hear you.
Hello? Yeah.
Okay.
So this is clear, no? This.
Yeah.
So now we come to angles. Okay. So angles, how do we represent? Okay. So think of this. If there is the origin here and there is Z1 here and there is Z2 here, right?
Hmm.
Z2 can be written as R2 EI theta 2, Z1 can be written as R1 EI theta 1, right?
Yeah.
So what it means is this angle is theta 1 and this angle is theta 2, right?
Hmm.
1 second, hold on.
Yeah.
Okay. So
Yeah.
this is my point, this is my point, right? So now
Hmm.
if I want to write this angle, right,
Yeah.
then I already can see from the figure that this is theta 2 minus theta 1, right?
Hmm. Yeah.
Correct.
Yeah.
So what we sort of know is that arc of Z2 minus arc of Z1, right, is
Hmm.
the angle between them, right?
Yeah.
Right?
Yeah.
Correct. So
Yeah.
this can be written as again arc of Z2 by Z1, right?
Oh yeah.
Right, is equal to the angle theta that is between them, right?
Hmm.
Correct. So
Yeah.
now what I have written here, arc of Z2 by Z1 can be thought of as Z2 minus 0 by Z1 minus 0, right? Why am I
Yeah.
mentioning the 0? Because the angle is always formed at a vertex, right?
Hmm.
This is the vertex in this case, right?
Yeah.
So think of it as two vectors. You can only form an angle if the two vectors are meeting at a point, right?
Yeah.
So that point is important to understand. Here the point is 0, so it is Z2 minus 0 is the direction of this complex vector, and
Hmm.
Z1 minus 0 is the direction of this complex vector, right?
Okay. Yeah.
So you have one vector like this, one vector like this. So this point is Z1, this point is 0, and this point is Z2, and this point is 0. So this vector
Hmm.
direction is argument of Z2 minus 0, and this vector direction is argument of Z1 minus 0, right?
Yeah.
Correct. So
Yeah.
then the difference between them is the angle that we seek, right?
Hmm.
So argument of this minus argument of this. So that becomes argument of Z2 minus 0 by Z1 minus 0, right?
Yeah.
Okay. So now, suppose the thing was not at the origin, right?
Hmm.
Suppose it was not at the origin and you had a triangle here, right? Z1, Z2, Z3, right?
Yeah.
In this case, I want to understand what is this angle, right?
Hmm.
Let's say I want to understand this angle. So again, you have to think of it as, let's see, this is a complex number like this Z2. This is a
Hmm.
vector. This is also a vector, right? Z1
Yeah.
vector. Each complex number can be thought of as a position vector, right?
Hmm. Yeah.
So the angle between them, this angle, is the exterior angle of this triangle, no?
Yeah.
Right? So that angle should be equal to this angle plus this angle, right?
Yeah.
Correct. Uh,
Wait, could you explain that part again?
this is exterior angle, no? In this triangle, let's label it A, B, C, O, right?
Yeah.
So if you extend it here, correct. So this angle is what we want, right?
Hmm.
So this is same as this, right?
Yeah.
Vertically opposite, right?
Yeah.
And this angle is the argument of Z2, no? This is arc Z2, right?
Yeah.
And this is theta that we want. And what was this big angle? This big angle was what? This was arc Z1, no?
Yeah.
Right? So, one second, I made a
But
mistake.
like, are OA and AC like the same line?
One second. So, this is like this, and this is like this, right?
Okay, yeah.
So, Z2, argument of Z2 is not that line, no? The problem is this.
Yeah. So instead of 0, it's like Z2 now, right?
One second, I'll just do it differently.
Yeah.
I'll just do it using the moving the origin. Okay, so
Okay.
let's see, this is Z1, this is Z2, this is Z3, right? Now I want this angle, okay? And earlier I have understood that whenever the angle was at the origin, right?
Yeah.
If this was Z3 and this was Z2, I can write this as argument of Z2 minus 0 by argument of Z3 minus 0, right?
Yeah.
Right. So the problem is that this is no longer the origin, right? Correct. That is the only
Yeah.
change, right? If
Yeah.
it was at the origin, then I'm sorted, no? So what I will do is I will move the origin to this point, right?
Okay.
I will move the origin to this point. If I move the origin to this point, Z2 becomes 0, right?
Yeah.
And Z3 will become Z3 minus Z2. Think about it. Z1 will become Z1 minus Z2. Why?
Okay, yeah, because the X and Y
This
are
is 1
changing.
comma 1, suppose, right?
Yeah.
And this is 2 comma 3, suppose. And this is 3 comma 4, suppose, before you changed it, right? And when you bring it to this will become 1 comma 2, no?
Okay, yeah, got
This will
it.
become 2 comma 3, right? We have to subtract it, no? Because your origin has shifted, right?
Yeah.
So now it is obvious. Now a new complex number is Z1 minus Z2 and Z3 minus Z2, right? And now this is the origin. So I have to just simply write Z1 minus Z2 by Z3 minus Z2. Because
Yeah.
minus 0 and minus 0, obviously. This minus this and this minus this argument, right?
Okay, yeah.
So basically what we are getting is any situation you have, if you want one particular angle here, right? So you have this vertex Z1, this vertex Z2, this vertex Z3. So shift your origin to that vertex and this will become Z3 minus Z1 and this will become Z2 minus Z1. No?
Yeah.
And go in an anti-clockwise sense. Anti-clockwise sense because all angles are measured in that direction, right? So more anti-clockwise one comes first and then less anti-clockwise one comes, right?
Okay, yeah.
So argument of Z3 minus Z1, which is more anti-clockwise, minus argument of Z2 minus Z1, right?
Yeah.
So that is the angle. So this is going to be Z3 minus Z1 by Z2 minus Z1, right? So notice that the vertex Z1 appears in both numerator and denominator. That is the point where the angle is formed.
Yeah.
Okay. If I wanted to find in the same figure, if I wanted to find this angle, right? Then I will move the origin to which point? This point, right?
Yeah, Z3.
So this will become Z1 minus Z3 and this will become Z2 minus Z3. You understand why, no?
Yeah.
And which is the more anti-clockwise side? This side is anti-clockwise, right?
Yeah.
So this will be argument of Z2 minus Z3 by Z1 minus Z3,
Okay. Yeah.
right? Similarly, if I want this point, right, then I will move
Hmm.
the origin to this location. So then each of the coordinates will become, originally this was called Z1, this was Z2, this was Z3, right?
Yeah.
So this is Z3 now. So this is 0. So this is Z2 minus Z3, and this is Z1 minus Z3, right?
Yeah.
And which is the more anti-clockwise side? Draw anti-clockwise direction, which is this, right?
Yeah.
Right. So argument of Z1 minus Z3 by Z2 minus Z3, right,
Okay. Yeah. Got it.
is this particular angle, right?
Hmm.
You understand?
Yeah. Got it.
If you reverse the clock, if you make by mistake this angle, you will get a reverse thing, right, which is negative
Hmm.
of that angle, right?
Yeah. Right.
Okay, so now what happens is, if I have to do a rotation, right, if I
Hmm.
have to do a rotation, now it is very obvious what you need to do. So suppose
Yeah.
this is Z1 and you have to go to Z2, which is at an angle of, the angle of rotation is alpha, okay?
Okay.
So initially, suppose this is R1 EI theta 1, then finally, if it is simple rotation, then distance will not change, no?
Hmm. Yeah.
If it is simple rotation, this distance will not change. This will also be R1 only, right? But it will be
Yeah.
EI theta 1 plus alpha, right?
Yeah.
Right? So the final point Z2 is equal to R1 EI theta 1 into EI alpha, right?
Hmm.
So Z2 is equal to Z1 into EI alpha, right?
Yeah. Okay.
Right?
Yeah. Got it.
This is written as Z2 by Z1 is equal to EI alpha, right? This is
Hmm.
rotation about the origin. See,
Oh yeah.
this is the same thing that we have written earlier also, no?
Hmm.
Rotation
Okay.
about the origin. So, however, if you wanted to rotation about some other point, right? So
Hmm.
let's say we have a figure like this, right? Z1, Z2, Z3, Z4, right?
Yeah.
And I want to rotate this trapezium or whatever figure about the vertex Z1, right?
Hmm.
By an angle of 30 degrees, right? In
Okay.
the anti-clockwise direction. Okay.
Yeah.
So it will be something like this now, let's say. Something different it will look like now,
Hmm.
right?
Yeah.
But I am rotating about Z1, right? So
Yeah.
first thing you should do is bring your origin to Z1, right?
Yeah.
So to bring your origin to Z1, first thing I will do is I will write this as 0. I will write this as Z2 minus Z1, Z3 minus Z1, Z4 minus Z1, right?
Yeah.
Now I have to do a simple rotation, right?
Hmm.
So right now unrotated, this point is the coordinate, right? These are the coordinates, right?
Yeah.
So final, so if I have Z as my unrotated point, right? After rotation, it should become Z is equal to R E I theta, let's say. After rotation, you should get Z dash is equal to R E I theta plus alpha, right?
Hmm. Yeah.
So it should be R E I theta into E I alpha, which is equal to Z into E I alpha, right?
Yeah.
If this was my unrotated point before, afterwards it should become this, right?
Hmm.
So my new coordinates will be Z dash for this point, right? For this point, new
Okay.
coordinate will be this, right? Z dash
Yeah.
is equal to initial point into e power I alpha, right? Initial point is Z2 minus Z1 in the new origin
Hmm.
into EI pi by 6, right?
Yeah.
You understand? So this is my vertex Z2 dash, right?
Hmm.
Z2 dash.
Okay. Yeah.
Z3 dash will become original point, which is Z3 minus Z1 into EI pi by 6, right? Z4
Hmm.
dash will
Yeah.
become original point Z4 into EI pi by 6, right? Okay.
Should it be Z1 minus Z1?
Oh, Z4 minus Z1, obviously,
Oh yeah, got it.
right? So
Yeah.
whenever you have to do rotation, think of it as a rotation first about the origin. That is very simple. Okay.
Hmm.
You just change the angle, right? You just change theta to theta
Yeah.
plus alpha, right? And if it is not about the origin, first do a translation to the origin to make it about the origin, right?
Yeah.
Wherever you have to rotate it about, right? Just move the origin to that point. So everything else will become minus z1, minus z1, minus z1, right?
Yeah.
And then do the same thing, then rotate it. If it was clockwise rotation, I would rotate it by minus alpha. So you will put minus alpha here, right?
Yeah.
Okay. So in the next maths class, what we'll do is we'll continue from here. There are some other things that we need to do. There's nth root of unity
Yeah.
and stuff. But you can try out the questions that are there in beginners box 4 or whatever is there, right? In the
Yeah.
next few sections and all. Okay.
Okay.
So try as many
Yeah.
questions as you can. Once you have doubts and all, we'll be able to discuss more productively.
Yeah.
Okay, that's all
Okay.
for now then.
Okay. Thank you.